one of the coolest ones.
Yeah, 100%. It's the one that makes the most sense to me at the moment.
That's good.
Yeah.
It's like it's one of the most powerful algorithms.
Right. But in general, it's just me like learning how to like because in a developer state of mind, like I understand how to approach a problem, how to debug, and like how to build things, and how to use different resources. But it's more of like when you're given a word problem, you have to implement math and then certain different elements. It kind of confuses me on that, and that's why I feel like I need something nice.
I think as a developer,
Okay, so going back to this, I tried to get the iPad and I couldn't get it working.
Couldn't get it to work.
I just want that skill in general. You know what I mean? That's why.
I mean, if you do something in research, then you
Do you have slides or no slides?
No,
Okay.
I didn't get around to it.
I'm trying to recreate it.
Okay.
So in a sense, I'm trying to do that, but with desktop apps, but I want it to be fine-tuned data to me. So I need to be able to train the data and one stuff. So
Yeah, you don't really need this stuff for that.
No? No. I would have thought that like machine learning AI is a lot more.
So remind me your name?
Daniel.
Daniel. Okay. Okay. All right. Well, Ricky assigned me two problems to work on. How many of you have taken theory of computing or theory of algorithms? No? Neither have you. So I think the first one is out. So let's do the geometry problem. Okay, sounds good. We'd have to pull this up. So I can pull it up here?
Yeah. Just open up Chrome. Yeah.
And
you can just open up a new tab.
what is it called? Convex. Oh, well, no. It's in the Is it already open here?
Yeah, it's a tab to the left.
One of these.
No, go back.
Go back. Yeah.
Just close the tab you created.
Close the tab I created. That one.
That one.
Okay.
Yeah, you can.
Giri is somewhere here.
Yeah, go.
Because you sent it to me, no?
Mm-hmm.
Oh, yeah. Okay. So it's not H, it's D, right?
D, yeah.
Okay. All right. Okay, guys, take a look at this problem. Can you read this, or do I need to make it bigger or smaller? Is okay. Is somebody outside the door?
I think I saw someone. But they
Yeah.
walked by.
They got scared, intimidated. You guys look too nerdy.
Oh, yeah.
No, they came back. Hi.
Hi.
Sorry,
Can you
Ricky,
be-
I don't
Yeah.
Sorry.
No worries.
Okay, read quickly. Oh, now I understand the name of this guy. His name is Euclid.
That's clever.
Mm. It's a little too wordy. You need to read the problem. You got it? Done? Oh, wow. Okay. Here's more. So can one of you summarize the problem? Ian, you want to give it a shot?
Sure. We need to create a convex hull that has one.
Right. And the point has to be such that
Well, it has to be an integer.
it has to add an extra point on the hull. Okay. There are points, if you add them, it'll actually reduce the number of points. Okay. So you want to make sure that it actually increases the number of points. So you want to count how many points increase the number of points on the hull. And let's see what the output is. And the output is?
All of the points that can extend.
Right. So an extend is something that looks like that red point there, right? Everyone clear about that? And what's an example of something that doesn't extend?
A point inside the sheet.
Point inside is one. Okay, what else? What about points outside? Are there points outside that don't extend? Because there's an infinite number of points outside. Should I just include everything?
There are some, I guess, that maybe one, you put one on top.
Yeah.
That would also be
Yeah, if you go way up on top, then, and if it's right on the y-axis, it's not going to increase the number of points because it'll actually decrease, it'll actually remove one of the points, right? So not all points increase the number of points on the hull. You want to know which points increase the number of points on the hull. Is this now clear? Yeah? Okay, good. And then we have constraints. So what are the constraints? Let's look at the constraints because that often determines the strategies we want, right? So we're told that n is between 3 and 50. So roughly there are 50 points at most on the hull, right? And we're given a grid that's 1,000 by 1,000. All right? Everyone understand the problem? Anyone over there not understanding the problem? Is this all clear? Because this is a time to ask. Don't ask me later.
One
Yeah.
question is the points that we choose, they can only be integer coordinates?
Right, that's right. So good point. Yeah, we are told that first of all the points we are already given are integer points, meaning the coordinates are integers, and the ones we need to look for need to be integer points because otherwise your points are infinite, right? Okay, everyone clear about the problem? Yes? Okay. So let's start with, I think we should try and, can you turn off one of the lights and maybe turn that one on? Yeah.
Well, one thing is,
Right?
Yeah, just have to.
Yeah, I'll take care of that.
Just like the glass thing.
The glass thing, right? Yeah, okay. So here is one thing that yeah, I don't know where to start. All right, so let's start with the big picture, and then we'll go to the small picture. So the big picture is that you're given a convex hull. You're given points that are already on the hull. Okay, this is a bunch of points that are on the hull, and you're asked, what things can where are the new points I can add to this that will actually increase the number of points on the hull? That's the question, and they have to be integer points. So there's a grid that's overlaid on it. Okay, I'm sorry, actually even the existing points need to be on the grid, so I didn't quite do that. There's more here, and so on. Okay, and then of course there's also vertical points. This is our scenario. Now, question is, what kind of points would increase the hull or increase the number of points on the hull, and what kind of points would not? So first of all, if it's inside the, as Ian pointed out, if it's inside the blue part, it's not going to increase the number of convex hull points. In fact, it's not going to add to the hull at all. So therefore, we can discard all of them. So these points here are irrelevant to us. So anything here is of no consequence, right? Where else are the inconsequential points? How do we eliminate portions of the space? Once we figure out where in the space things will actually increase, then we can go and look for integer points or points with integer coordinates and then count them. Okay, that's the general plan. So question is, where are these points? Any thoughts on this other than Ricky?
You could draw a rectangle that encompasses the leftmost, rightmost, topmost one.
I could draw a rectangle. So actually, let me simplify the problem in order to make this discussion clearer. So let's start with a triangle instead of anything fancy. All right. Now my question is, where should I add a point? Where can my point lie in order to make this a quadrilateral? Quadrilateral? Yeah, quadrilateral. Any thoughts on this? Make it quick. We don't have all day.
Well, you take the leftmost x, rightmost x,
Yeah.
topmost.
So you're saying make a box.
You could even
Make a bounding box. Is that what you're saying?
Yeah.
Do that. And what are you saying? You're saying that anything outside this bounding box, I don't need to worry?
No, that's your target, no? You
Is
don't
it?
want it to be, you don't want it to cut within itself, right? You said it has to stay convex.
I'm going to ignore anything here. We already discussed that.
Yeah.
But still, there's portions here and there's portions here. There's more. What my question is, where am I going to find valid candidates to add? How do I find these regions? So I would say, stop thinking about these rectangular blocks. That's a bad idea for you. That's my hint. This will only mess you up. Thinks, yeah.
If it is in a grid, then it would be the quadrants.
Forget grid. There is no, I'm not even giving you grid. I'm asking you a simple question. Where are any points that will increase the convex hull? Maybe, meaning it'll make it a quadrilateral. Tell me where they are. Can any point work out? Obviously not, right? Obviously a point here is not going to work out. Why is that?
It will create a triangle.
Right, but I need a better reason than that.
Can we look for a point that doesn't lie on those three lines?
On those three lines. Okay, so you're saying extend these lines.
Like
Is that what you're saying?
Yeah, anywhere,
Okay.
any point that doesn't lie on those three lines
Uh-huh.
is a candidate.
Well, so is the pink point I just drew. It's not on any line. This guy here, is it a candidate for adding? Yes?
Depends on where exactly it is.
It is exactly there. That's all I
Will it
need to.
not form a four-sided figure?
Absolutely not. There's no chance in hell
Or
because
it has to go from that point.
because it'll go here. It'll go like that. Right?
It's right above the first point.
So, yeah, you're going to say something?
I was gonna say that what if we could just, in a sense, get the symmetrical version and flip it and then anything
Symmetrical version of the triangle?
If you were to say,
Of the triangle, did you
yes,
say?
of the triangle.
Uh-huh.
So that would mean that anything from.
You're saying take a reflection of this triangle and then what?
Well, if we make a reflection of the triangle, we already have a quadrilateral. But if we were to just choose one point.
Why? What purpose does the reflection serve for you?
Well, if
How
we
did it
did-
help you?
If we did the reflection in the sense of the in between the actual triangle. So if we were to draw a line through the middle of the triangle, anything from the left to the right.
Uh-huh.
A valid point to make a quadrilateral. In a sense, to make it, for example,
hold your, so continue to think along those lines. Let me go to somebody else and look at some other suggestions.
The points which are opposite, like opposite to an angle.
What does that mean?
The one which you have drawn.
Sorry?
The one, the
Tell me with respect to let's name the points here. Here's A, B, and C. Okay?
Any points
Yeah.
which are lying outside AB or AC or C. Like it could be like the suggestion which will be given, like the lines.
The two lines I've drawn on top.
Sorry, the line AC and BA, the intersection, like the one
AC and
BA.
AC and AB. Okay.
AB basically.
Yeah. Uh-huh.
So the region which is marked over the above region,
Uh-huh.
the point should be ignored from that.
Should I should ignore them?
Yeah.
Okay.
Similarly,
Yeah.
the points on the another vertex, yeah.
You want to ignore that?
Yeah.
And
the ones on this side.
you want to ignore this?
Yes. And any point outside the remaining region
This works.
that could.
Does everyone agree with this? You like what he's saying?
I do like what he's saying.
Oh, you like what he's saying? Okay, you got one vote. The others they don't care. Srimants, what do you think? What?
That reason if you take a point parallel with the point.
Where? Where? Over here? On top? Sorry?
Be eliminated.
Those will be eliminated.
No, let me finish this thought. Go ahead. Your question is probably there with others as well, and they're not talking.
So I'm thinking like.
No, tell me your question.
No, my question is not that. I'm thinking like, as you said, you can ignore that, right?
Yeah. You're not sure why.
Yeah.
Okay, ask that.
Yeah, that's what I mean to say.
Yeah, so answer his question, sir.
So if the point, if there any point in those regions.
Yeah, I picked one.
Yeah.
Yeah.
They are probably gonna create a.
Probably. No, probably is no good.
Those are going to create a triangle.
So if I now do a convex hull with this point and the three old points, what do I get? I get a triangle. That's no good. I need a quadrilateral, right? Srimant, is that clear? What about here? Same thing. What about here? Same thing. So, are you with him or not with him? With him. Okay. So, so this is a starting point for you. So therefore, anything in these regions are perfectly okay to increase the number of points. Is that true? Yes. Okay, good. So if you started with a triangle, you actually have infinite number of points. It's not going to help you. Okay, fine. So let's assume that we know the answer for at least this kind of triangle. There may be other strange kinds of triangles where that's not quite true. Well, we'll see. Yeah? Can I erase the triangle part now? Okay. Now let's go back to our polygon. Now tell me, now generalize what you thought. Well, maybe I don't want to erase this. Now tell me, where are the points I need to look for?
We do the same thing.
Yes. What? Tell me exactly what you do.
All of the,
Extend all the lines, right?
and the part where they,
And then throw away those strange parts. So I'm going to extend this. I'm going to extend this, and then I throw away. So all of this becomes throwaway, right? Is this clear? Okay. Now, in the end, after throwing away, what am I left with?
Triangles.
Triangles?
Not triangle as well, but the regional triangle.
Are you sure? Are you sure it's not triangles?
it should be triangles because it is
So if I do it over here, what do I get? and then over here. So I am just extending these. So what should I do outside this? Anybody?
Can you use a different color to draw those lines? Maybe?
You make my life hard. I put in so much effort to draw nice ones. Okay, let's use, yeah. So you're saying, now what? I did what you asked me. Points inside the triangles,
Yeah, but outside the.
but outside the polygon, right? So therefore, that would be, yeah, I used the wrong color here for the inside. This is all stuff I want to throw away, right? And so what I want to keep is, I want to keep all this, right? Are you with me? So if I can compute all the integer points in those regions, my job is done, right? Not quite.
So, going back to the triangle.
Yeah.
This is what I'm thinking in my head. That seems fine to me. But
Yeah.
erasing those blue parts is okay.
Yeah.
But why is only keeping the green fine?
Because we can show that you pick any point in that green area, you'll have 4 points on the hull. You're not convinced. You want the triangle back? Triangle was here, and I threw away, well, you know what I threw away. And this was anything that doesn't touch the lines, but that's in this green part, I'm saying will increase the number of points on the hull. You don't believe this?
I mean, I believe this, but
Yeah.
what property of like a convex hull guarantees this?
What property of convex hull guarantees this? Okay, good question. Anyone wants to help me or help answer that question? Are there any properties of the convex hull that we can use? How do we prove anything about the convex hull?
You pick 2 points and then draw a line.
Sorry?
You pick 2 interior points and then.
That's true, yeah. So a convex hull consists of set of points. That's a slightly abstract definition, but we can go with it. Where if we join those 2 points with a straight line, the entire straight line segment needs to lie within it. That's one thing. But there are actually other nice properties that you can think of. One is that if you have a convex hull, if you traverse it in one direction, then first of all, the interior is always on one side. It's always a right turn. Always the angles are sorry?
Negative, going clockwise.
Well, yeah, so it's always a clockwise turn at each vertex. These are things that you can prove relatively easily.
Yeah.
And I'm going to try and prove that with the 4 points that I have. Okay. So you pick a point here, whatever you like. Let's say I pick that point. I'm going to show to you that over here, that as I traverse this, I am going to have right turns. And when I go from here to here, well, whatever it is, then from here, I'm going to insert that point between this and between this point and this point, right?
Yeah.
So that's going to be, because it is it is to the right of that line, it's going to be a right turn.
Okay.
And therefore, that's going to be a right turn. Then from you can do it the other way around and show that when you get here, this is a left turn, and therefore, in the end, when you go from here to there, it's going to be a right turn. And that's enough to prove that it's going to be a convex hull, and that point is going to be on it. And we can show, we know that nothing is collinear because it says so on the problem, and that at all these vertices you're making a consistent right turn, and therefore it's a convex hull. So one of the properties of the convex hull, which we assumed in what I just said, was that if you traverse the convex hull in specific order, in the order in which it shows up, you're always going to make right turns. Okay? If you traverse it in the opposite direction, it's always going to be a left turn. You'll never have a right turn followed by a left turn. That's not going to happen. Okay? So convex hulls have this property, and therefore you can use that to prove a variety of things. Okay? We focus on the picture on the left, and we've identified regions where we can find candidate points, and all we have to do is to count the number of integer points there. Now, counting integer points there is a real pain if you don't know how to handle it. So that's what we have to kind of focus on next. So at this point, it's just a matter of implementing things. But before that, we should think about when you would get infinite number of points, when you're simply not going to be able to count, or when there's just too many. Are there simple criteria for deciding that the number of points are infinite? Because the problem asks for it. Or give me one example where you'll have infinite with, let's say, 6 points.
When the lines you're extending,
Yeah.
they don't meet.
Very good. So if the lines don't meet, then you're never going to have that triangle, right? So if they go and diverge, or if they are parallel, then you're stuck. So when would you have two sides of the polygon either being parallel or diverging away? Is that possible? Square. Square is a good example, rectangle, whatever. Or if you have two parallel sides, and then this other side, you can have whatever you like, right? This is a convex hull, but here the two sides are parallel to each other, and so therefore when you extend them, they're never going to meet, so you don't have a triangle. So therefore, you can immediately decide it's infinite. There are other cases as well. If instead of being parallel, if they diverge away, then you have the same problem, right? That also is possible. So I could have something like that, and over here I can do whatever I want. This is also an example where it's going to diverge away instead of converging, and you're never going to have that triangle. So if you find two edges separated by another edge that are either parallel or diverge away, then you're done. Then you can just report infinity and stop. Is this clear? So that's a separate test. We'd have to do that test right at the start and decide that it's infinite. And if it's infinite, then you don't have to do any counting. You can stop right there. Otherwise, you have to actually go and count the number of integer points for which this thing can happen. Are you with me so far? All good? Yes? Okay. So the next headache is to kind of go and count. So you have to first find these triangles, then you have to go and count them. Now, in order to count them, you have to identify the triangles. But the triangles are, well, for every triangle, two of the points are on the polygon, right? And the third point is somewhere else. That's the meeting point of two of the edges extended to infinity. So theoretically, here's one way to do it. I identify the triangle, I already have 2 of the points. I take the 2 edges that are to the side of it, that one there and that one there, extend it, find the coordinates of this point. Finding the intersection point of 2 lines is possible. So then I have the three points of the triangle. Then all I have to do is to list out all the integer coordinates of the points inside that triangle. Okay, conceptually that seems doable, right? And I can do that for each triangle, and we know that if the polygon has n points, there are going to be n such triangles, right? And each one has to be a triangle, by the way, because if it's anything else, it's infinite, right? Okay. Now, what we are told is that, well, what are the challenges here? Do you see any problems in doing this? What are the problem constraints?
The number of sides?
The number of sides you were told is at most 50. Is that a problem? Doesn't seem like it. That's not really the problem. So it's the other number that's the problem. What's that? How big is the grid? You're told that all the points are within a 1000 by 1000 grid. So remember, it's only the coordinates of the polygon. So what you're told is that all the points of the polygon, which is this, and this, they are within the 1000 by 1000 grid. Nobody has told you where these intersection points are. This could be far, far away, which is an annoying thing, which is going to bother us a little bit as we move forward. Okay? Yeah.
Bother us as in counting the integers?
Yeah.
Okay.
So essentially, we are going to, at this point, we are going to simply say, if we can write a small function that where if I give you 3 points and it counts you all the integer points, then I'm done, right? I'm essentially done with the problem. But the question is, what is that process going to be for counting? Is it going to be brute force counting, or is there some magic formula that you're going to write down and spit out a number? Well, the good thing is that 2 of the points of the triangle are sure to have integer coordinates, which actually helps. But the third point, you have no guarantees. It could be anything. It could be, it can't be irrational, but it has to be a rational number. Okay? So these are our challenges. Now we have kind of boiled it down to a simple problem that says, I give you 3 points. Tell me how many integer points there are within that triangle. So this is my current problem. I give you these 3 points. We'll call it, I don't know, A, B, and C. And your job is simply to count how many integer points there are here. Now, I'm going to try and show you a brute force solution, which you'll see that it doesn't totally work. Okay? Or maybe it works. You guys can tell me. So the brute force is, I take my entire 1000 by 1000 grid. How many points are there? Sorry? How many points? A million. Right? 10 to the 3, 10 times to the 3. Million points. Right? Million points, I can go and look at each one of them if I want to. It's not such a big deal. So I could take each of those million points and then do what? Check if it's inside my triangle. Right? By the way, let's take a small diversion and say I give you a triangle and I give you a point, and my question is it inside the triangle or not? How do I do this? Srimant is going to tell us. Yeah?
There is an algorithm called ray casting algorithm.
What? Ray casting. Wow, you're way off.
No, so the idea is like you count how many intersections. If you draw a line, it does with the polygon. If it's even, it's outside. It's inside.
I've taught you better than this. Anyone?
Use left turn test.
Yes. So it's a simple left turn test which also works for polygons, and the idea is we don't know whether the point is here or here or here. Okay. So it's either inside or outside. And we want to know whether it's inside the triangle or outside the triangle. So here is the way you go about it. Let's say the point is x. Well, no, it's inside I've drawn a cross here. Let's call this point as P. If I go from P to the first point in the triangle, that's A, and then to C, we'll determine whether it's a left turn or a right turn. In this case, it's a right turn, right? I'm going to go from P to C to the next guy there, and that's B. This also needs to be a right turn, and then P to B to A also needs to be a right turn. Either all three need to be right turns or all three need to be left turns. If this happens, then the point is guaranteed to be inside the triangle. And this is called this is a standard trick that people use for left turn and right turn tests. If it is outside, what will happen is P to A to C is a right turn, P to C to B is a right turn, but then P to B to A ends up being a left turn. Is that clear? So your left turn test will fail if it's outside. If it is here, same thing, you can go through and check for yourself. So you need consistent directions when you go to adjacent points on your polygon. And if it's inside, you'll get a consistent turn, depending on whether you traverse it clockwise or counterclockwise. So I can take any point I want, and I can check whether it's inside my triangle. So here's one possible solution. I go and look at every point on my grid, million points, no big deal. And for each one of them, I check whether it's in my triangle. And by the way, the left turn tests are incredibly easy, and I can show you separately how to do that. Any problems you see with this approach? Sounds good to me, no? So if I want to just count how many points are inside this, I just go through the entire brute force. I look at every point on my grid, check if it's inside the triangle, and just count them. I'll get a count. At the end, I'm done. What's the problem?
Don't you have to do it for every triangle? You're checking a million?
Good. Yeah. So excellent point. It's not just one triangle. I have to do this for many triangles, but we know it's only 50. So we still are talking about 50 million. There's a good chance I can do it.
Why can't we limit our testing?
There are lots of ways we can improve it, but that's not my question. Focus back on whether this works in the first place.
Maybe outside the grid.
The problem is that your A, B, and C, one of the points, which is these intersection points, may be outside my grid. Does this make sense? This causes trouble. So if this problem were not there, then my algorithm is somewhat simple. Brute force, look at every point on my grid. For every triangle, I just count, and I'll be done. Now, if you don't want to do this 50 million times, there are ways to improve it, and I can show you those tricks, but But first, we have to ask the basic question, does it work? And we have the answer. It's no. It doesn't work. And that's because one of the points of the triangle itself is outside the grid. What are you going to point? What are you going to do? That means that there are valid points that you have to count that are outside the grid. And that's where our main problem is. That means we really have to do something else in order to do this counting. Yeah, it's.
Can't we find the point of intersection of those two lines and see if it's outside the grid? And
Yeah.
if it is, only for those we are not.
And for those, what are you going to do?
Then you can limit yourself to, you can find points that lie on the grid that would be
Okay.
the boundary condition.
Yeah. Yeah. The problem is that there is no bound on how far away that point is. Okay. Remember, when it's parallel, right, that point is at infinity, right? I can just make it epsilon whatever, and the point is still going to be super, super far away, somewhere near the moon. And I would have a lot of points to count. Yeah, all you need to do is to think about it this way. If it's perfectly parallel, you extend them, and here is an edge, right? You extend them, this goes off to infinity. So they are never going to meet. There is no intersection point. Now all I have to do is to make this just tilt this just a little bit, right? And yeah, it's going off to way off there. And that's going to cost you a lot of heartache. So it turns out that you have to do something else. Now, in order to do something else, part of the trick is to know that that two of the points are integer points, and that's where everything works out for you. Otherwise, you're dead meat. What I want to see is, barring this problem, by the way, I have not figured this out completely, or we can try it out here. There are no guarantees it'll all work out. But barring this particular problem of where one of the points is outside my grid somewhere far away, do you understand how this problem is solved? Yes? Okay with it? All right. So essentially we are left with this basic problem where you're given a triangle. The nice thing about the triangle is that two of the points are integer points. So meaning they have integer coordinates. I'm going to make them uppercase A and B. But the C, I can't even tell it's lowercase. Let me change that. Let me call it something else. So let me call this x0. No, I don't like it. What do we want to call this?
Q and R.
You want P, Q, and R. Okay. So then I have P, I have Q, and I have lowercase r. So lowercase r may have non-integer coordinates. Okay. But P and Q are nice, well-behaved points. They have integer coordinates. Now all I need to do is to count the number of integer points in this region. Any thoughts on how to do this?
This is what I am thinking, like between P and Q, suppose we have n integer points.
Yes.
If we go
Very good.
one level up,
Yes.
then we have n minus 1 point. This is what I am thinking.
Yeah. So you want to reduce this until it all vanishes away. This is what you're saying. So you're saying count the number of points here. and then let it slowly fade away, and you can kind of look at, well, you can figure out at what rate it fades away or something like this, and you keep adding until until you get it.
You could do run and rise one by one.
Sorry?
Run one, rise one, run one, rise one.
Run one, rise one means you'll have to go all the way to wherever this point R is, and that we know could be sitting on the moon. Right? Same problem. It's as bad as counting.
Just a small question, like, do we know the boundary or no?
Boundary of what?
They mentioned at 1,000, right, the boundary.
Yes.
So do we know that, or like any coordinate specific or no?
No, I am happy with 1,000 by 1,000. I don't have a problem. That's well defined boundary for me. The problem is not my points from the convex hull. Again, you're not getting it. These guys are my points on the convex hull, right? Let me put them as squares. These guys are convex hull points. They are well behaved. They are within my 1,000 by 1,000 grid. The problem is when I extended these lines, I created new points, which I have no idea how far away it is. These guys. This one is already looks pretty far away to me. Okay, and there may be lots of integer points here. And it keeps going down and down and down, and you have to keep counting until you get the answer. So one good thing is that the number of integer points are tapering in a well-defined way. So there are various ways to do this. If you want, you can, yeah. I'm going to erase this left part now, okay? Because all that is pretty clear, right? Yes?
Yeah.
Okay. So one of our first tricks is going to be to put the good guys on the x-axis. So P and Q are good guys. They have integer coordinates, right? I'm going to put them on the x-axis. So they're going to look something like this. And I'm going to put the P at the origin and Q somewhere. And we know that Q can't be more than 1,000 units away, right? So the main problem is with R, which could be anywhere, but it could be very far away here. It could be very far away here. We just don't know where it is. Okay, so let's just say this is R. What we know is that the nice thing is that actually let's assume it's this guy here. It's going to look something like this. That's our triangle. Okay, so I've reoriented the triangle so that it sits on the x-axis. Now here's the nice part, and this is related to what Yash was suggesting. We know exactly how many points, integer points there are on the x-axis between P and Q because we have their coordinates, right? Well, you have to remember that originally they were not necessarily on the same x coordinate, so these points may not be every unit away. It may be quite far away. You have to kind of figure this out, and it's possible to figure that out. So, but we know we can count how many integer points there are between P and Q on that line segment. Now, what we also know is that well, we've rotated things now, so but we've rotated things. We're not going to go horizontally up, are we? Yeah, this is sort of annoying. Yeah, that's not good. Yeah, no, let me rethink this part. Right, so so P and Q are sitting somewhere. Here's P, here's Q, and somewhere far away is R. Right? By the way, P and Q, this line segment PQ, it's possible that there are no integer points on that line itself. So we have to be very careful here. This is one of the challenging parts of this operation. Oh yeah, what do we do now? So the grid said something like this. Okay, and there are and then yeah, then there's more.
Instead of looking at PQ, why not start at P and go parallel to the x-axis to find the next closest integer point?
Yeah.
I think the key is to locate the first integer point.
Well, yeah. I mean, ultimately, those are all grid points. So finding near-guide things is easy. That's the challenge is to. My idea was to sweep this line along this direction and then figure out all the integer coordinates it hits. Is that even feasible? Yeah. Yeah. Okay. Yeah. I think. Yeah. Right.
I have a wild guess.
Yeah.
Basically, we know the lines are somewhere on the grid, and is it possible by any chance like we get the line formula? I mean, this.
Oh, the equation of the line is not a problem. Yeah.
Yeah, we get.
Sure.
We get the slope also.
Yes. Yes.
And we get the slope of both the lines.
Yes.
And any points within that range of that slope that we can be counted.
Doesn't help you with integer points. In fact, that was my first approach. My first approach was to do this completely analytically. And the problem with it is that in the end, you're going to get linear equations. And linear equations don't help you with integer points. In the end, you just have to go and count somewhere. And that means looking through a set of integer values, and you don't know what integer values to stop at.
That would be to stop at would be the point where both the slopes, I mean both the lines intersect. That would be.
Yes, but over here the problem is that the y grid lines come like this, right? And for me to find all these intersection points is quite a challenge.
Professor, I'm just kind of spitballing, but could you take the 3 right angle triangles that surround that triangle and calculate what they are, and then see if the points fit in there? You know what I mean?
Okay, that's a good idea. That's a good idea. So you're saying I could take a parallel line here, and essentially that'll give me a parallelogram, and maybe count the number of points here, and then just take half of that. Why can't I do that?
Well, if you look at the origin at 0, 0, there's that right angle triangle.
So let me ask you this question. If I place the rectangle nicely aligned to the axis, I know exactly how many points are in it. But when I tilt it, is the number of points going to change, or is it going to stay the same? You sure? Yeah? I don't know. I don't know this. Yeah, I don't know this.
I think I've seen the same exact problem with the actual rectangle. I think it does change.
I think it's much smaller.
Well, let's because if we make the rectangle really thin, then we can twist it just a little bit, and it'll miss everything, right? If we make it just one unit wide, now it has well, let's make it 2 units wide. Now it has all these points in the middle here, right? It has an entire row, right? And now if I tilt it, there's no way it's going to capture the same number of points.
Yeah, that's what I was thinking.
There's just no way. So this idea of triangle thing is, but you're the yeah.
I think we could start with another assumption though, which is that you would have half. So if we could know in a rectangle that's positioned.
So if we can do this for a rectangle, it's as good as doing it for a triangle, because we could divide it by a half. That's good. That's a good idea. Except that we have to figure out how many lie on the line, but we can deal with that. Yeah, we can deal with that. You're absolutely right. So how about an easier problem? So you're saying, forget about this. Let's do an easier problem of rectangle. If we do the rectangle, sorry, not a rectangle. Actually, it's a parallelogram. Thank you. And in fact, the parallelogram is going to look like that, and 2 of these points are going to be weird. They're not going to have integer coordinates. Oh wait, wouldn't this have? No, can't. Yeah. I'd have to go and look for this. I don't have good answers. Or you should ask Ricky here. But he doesn't look like he knows the answer either.
This is one of the problems that stumped me. I had no place to start.
Yeah, that's why you gave it to me.
Maybe one thing to say, I don't know if this helps, is if we look at the specific problem of we have P and Q and we know they're at integer points.
Yeah.
And we're actually counting
Yeah.
the amount of integers.
Yeah.
I think if you take the slope, you find the LCM. You look at the distance and you divide by the LCM. You take the floor, that's the number of points. And maybe since it's a rectangle or parallelogram, that tells you something. You can come up with some formula.
All right, let's play with something else. So I'm going to erase this because we kind of understand the problem is now somewhere else, right? Um, um, so P and Q are integer guys. We also know how many points are on that line. Okay. Now, all we need to know is where the grid is with respect to this PQ. So here's the grid. Actually, let me draw the grid in red. Am I out of time already?
No.
Okay. So, essentially, the grid means that all your lines are vertical and horizontal, and your P and Q are going to sit something like this, right? It's going to be at some strange angle, sitting somewhere, right? And we know that P and Q are on grid lines. And there may be many other grid lines in between. Okay. Now, what happens when we move this line in that direction? Can't we capture all the integer points as we go along? Because we know the equation of this line, right? So it's something ax plus by equals I don't know, ax plus by, or you like y equals mx. Okay, fine. So y equals mx plus c. Essentially, as you move this, the c will become c plus extra, right? So your c keeps going up, but the slope remains the same. So c, as long as you keep increasing c, and if you do it in a steady fashion so that you capture all your points, you're done. Now,
Bounded by the left two the other two lines.
no, well, we'll get there. Give me a second. My question is, how much should I move this by before I hit another integer point? Can we capture that? Because if that is so, then I can sweep it and capture all my points. So either I should hit a horizontal line, or I should hit I have to hit both a horizontal line and a vertical line, right? And the question is, where would I do this? So let's say that I have y1 equals mx1 plus c. So here's a point on this line segment. So it might be either P or Q or something in between. Then I want to do so whatever that point is, I want to see when I'll hit the next guy. So that would be at y1 plus 1 and x1 plus 1.
Does it have to be touching the both axes?
No, I'm just counting those guys, let's say, right? Well, I will have something at y1 and x1 plus 1. I will have something at y1 plus 1 and x1, but I will also have something at y1. Yeah, so you're right. So that doesn't quite work out. So either it's going to be at y1 plus 1, or it's going to be at x1 plus 1, or both. And either one, with y1, my c is going to go up by 1. For x1 plus 1, it has to go up by 1 over m, right? if I increase C by 1 over M, I will hit the next horizontal line, right? Or if I increase C by 1, I will hit the next vertical line. Sorry, the other way around. If I increase C by 1, I'll hit the next horizontal line. If I increase C by 1 over M, I'll hit the next vertical line. And what? So what?
I think the thing that we're looking for is a constant rate of change between the amount of points that we capture and the slope of the line, right?
Yeah.
And wouldn't that be?
Well, what I was trying to get at was, is there a value of C to increase it by so that I capture every integer point? And it's unclear if I can figure that out, because it varies. Is it?
Can we check that estimation against the real line?
Sorry?
Can we check this estimation against the real line? And use the real line as a boundary for it?
Well, these are real lines, so I'm not sure I follow you.
Oh, I thought this was like an estimation of all the points.
There is no estimation here. What I'm saying is, here is my P. Somewhere here is my P, right? Somewhere here is my Q. Fine?
Yeah.
And there is a triangle here with a third point, which, I don't know, can be very far away. Fine? And all I'm saying is, I can sweep this line until it gets to this point R. Let's call this R. And keep it parallel all the time. Okay? But along the way, anytime it hits some integer points, I'm going to count them. And if it stays within my
So which lines are parallel? Like P to P and Q are going to be.
P and Q is going to stay at the same slope. I don't want to change that.
Right.
I'm just sweeping it. Okay? If you want, you can think of this as an infinite line. All right? And as it moves, it hits all the integer points that are of relevance, and I will count them.
Okay. Yeah, because I was thinking there's like, you're going to get another triangle that's
Right, right.
smaller.
So yeah, what I was saying was that every so often, either I'm going to hit a X grid or a Y grid, a vertical line or a horizontal line. And I know exactly when that will happen. And can't I just count this? And I have to do this 50 times. It's not such a big deal, as long as it doesn't go too far away. And R is a rational number, and okay, let's figure out what R's coordinates are going to be. Fine?
Yeah.
All right, let's do that. So, can we find this point R? You guys want to help me? This can get hairy. So remember, I have the polygon, right? And I'm looking at some part of the polygon that looks like this. There are two turns, right? And I'm taking this point, the first line here. Well, I better use different colors because you guys won't like it. So here is the first line. Then here's the second line. And here's the third line. Okay? I'm going to extend these lines. And remember, this is my P and this is my Q. Okay? And overlaying all of this, there's the vertical lines and the horizontal line grid, right? Okay. Then what I'm trying to do now is to find the coordinates of this guy. Well, all this doesn't matter. I've got two equations. One is the equation of this blue line. I'm going to write that as, I don't know, oh, you like y equals mx plus c. Okay. Y equals, sorry?
You just solve the two.
Mx plus c1. And the second one is going to be a yellow line. It's going to be y equals m2x plus c2, right? So you solve these. Essentially, you subtract one from the other, and you'll get x equals negative of c1 minus c2 divided by m1 minus m2. Or is it? Well, it's either a minus or a plus of this. Okay.
Once you have it, you can solve for y.
So essentially, this is. But then the question is, how bad can the slope be? The slope can be. If you have integer coordinates for the points, how big can the slope be? Or I want to know how big the numbers can be. Are you guys thinking?
Okay, what if you're starting point 0?
So yeah, so if in fact this is why it's better to write this as ax1 plus by1. Sorry, ax plus by. No, what? a1x plus b1y plus c1 equals 0. If this is the, and we know that this can be written with integer coordinates, sorry, with integer coefficients, and the coefficients are going to be within 1 and 1,000, right? Isn't that true? No, that's not necessarily true either. Okay, forget that. So if I have 2 points, let's call this A1, not A1. Yeah, A1, B1 is 1 point, and A2, B2 is another point. If I if I find the equation of the line through this, what is the equation of the line? Y equals, the slope is B2 minus B1 divided by A2 minus A1, right? Times x plus C is, what is C? Figure that out. If A1, B1 goes through this, x equals A1, what am I going to get? If x equals A1, then y is equal to, y needs to be B1.
You could use
right?
the other equation, y minus y1 is m times x minus x1. That's the other form of
So I want B1 to be equal to B2 minus B1 divided by A2 minus A1 times A1 plus C. So C is equal to B1 minus this term, right? Did I get this right? So A2 minus A1 is the denominator, and I will get B1 A2 minus B1 A1 minus B2 A1 plus B1 A1. What happened? What things go away? B1 A1 will go away, and so I get B1 A2 minus B2 A1 divided by A2 minus A1. So this tells us now everything we need, because what will happen is we are told that A1 and A2 are numbers between 0 and 1,000, right? Or 1,000 by, it's 1,000 by 1,000 grid. So it's some number between 0 and 1,000. So this number can be as big as 1,000. This number can be as big as 1,000. So therefore, the C part can be as bad as 1,000,000. Or at least it's a rational number where one of the numbers could be as bad as 1,000,000. This is bad news. Right. doing on time? Only 4 minutes left.
Yes, hey, sorry.
Bye. I don't see this happening now. I do have to think about it, but I'm trying to see if I can get some ideas to think about later. So we could write the coordinates of R as some rational number, and there could be a simple formula for it. And that's doable. But then what? What we can do is to break up this triangle so that you have a vertical line that goes like this, and now you have two triangles, the one over here and one over here. And now you have vertical lines sweeping this way, and all you have to do is to kind of figure this out. So that's another way to do this, and you can figure out exactly how many points are on this line, right? Because it's a vertical line, you can figure out exactly what points are on it, and that can be done even with brute force, no harm done, and it's all within the grid, so that can be done. And then so actually you can count this part quite easily because it's all within the grid, and I can go and spend all the time I need to swipe it. It's this part that's the problem. But if I can figure out how many points are here, am I able to then figure out how much it goes down by? Because I know the slopes of these lines, I know exactly how quickly it will go down. All right, so here is my strategy, which I'm going to have to go home and figure out the details. Did everyone understand what I did here with this vertical line? Or did I lose you? Should I repeat it? Repeat it? Yes. Okay, so first of all, here's my triangle. I'm just drawing it this way. P and Q are my points with integer coordinates. R is this bizarre guy with who knows what, rational coordinates, right? Then I draw a vertical line from Q or from P that hits the other end of the triangle. Okay, this is vertical, meaning it's vertical with the grid. Okay, and I will, which means that, remember, all of this is within the general grid, right? P and Q are inside your 1000 by 1000 grid, and so they're well behaved, and so is all these points. So I can do brute force to figure out how many points are on this line. Okay, and I can also do brute force for everything inside here and count them because they're all within my grid. All right. All I'm left with is this side, which kind of extends too far away. It could go well beyond outside the grid, and those are the ones that cause me trouble. Now, what I have to do is to figure out. Remember, as the vertical lines go, as you sweep the vertical lines, this number will go down by 1. After a while, it'll go down by 1. After another while, it'll go down by 1. After another while, it'll go down by 1. But it has to go down in a predictable manner. Because we know, since we know the slopes of the two lines, we know in how much time it'll go down by 1. And so that's how I plan to attack this.
Can we do the same with, like, you draw a vertical vertical line from Q to follow the P, then we draw a line from
Meaning?
the point which is intersecting P and R.
Yeah.
We draw a vertical line from that point all the way to Q and R.
Meaning
The point which is intersecting P and R.
here, this guy.
Yeah. We draw a line which is intersecting Q and R, and it should be perpendicular.
Like that?
Yeah, and it should be perpendicular to Q and R, or okay. Like I'm thinking that if we can do it in a recurrent way.
Yeah, maybe. Yeah.
Maybe a wild idea, but I'm saying that before we were looking at like bounding this with respect to R, maybe get really far.
Yeah.
But I'm saying one of the dimensions is going to be small, at most 1,000, and in this way we can always sort of make lines, and if we come up with some nice formula or some way of calculating.
No, look, his idea may actually work out because essentially this now we since we have two sides of this triangle as one being horizontal and one being vertical, I only have to deal with this slope. So counting here becomes very, very doable. It's a lot simpler formula now. Okay. Sorry? No. Now you're off on some triangle. No, I'm not answering your question yet. Let's focus here, right? So supposing I can do this, then I draw a vertical line from here, and I do that.
Mm-hmm.
Then I draw another horizontal line from here, and I do that. And I keep doing this until one of my triangles becomes 0, and then I can stop.
So the only hard triangle is the first one.
Sorry? The only hard, well, the hard one, that I can do using brute force. It's not hard, actually. I like this. I'm going to think about this more. This could work out. Or there might be a simpler way to do it. Yes, Jonathan?
Well, just an observation. It seems
Yeah.
like we're just leveraging the linear equation.
Yeah, absolutely.
Isn't there some way we could use like SOHCAHTOA or some more advanced trigonometry?
Such as what?
Like SOHCAHTOA sine over.
The problem is that we are talking about integer points. This is where everything breaks down. I can do lengths of lines and so on very, very easily. We need to know where are the integer points, and those can be anywhere. And that's where the problem is. Finding areas of these triangles, all that is easy because we have all the formulae in the world. But this is sitting on top of a grid, and we have to count just those grid points, and that's where the problem is. And some of those but if the grid point is sitting on this line, we can't count it. So there are all sorts of annoying things, right? We have to be somewhat careful, and at the same time, we have to kind of understand what we are doing.
So how do we find the point at which the vertical line intersects the line from P to?
Oh, you mean over here?
Yeah, that point.
Right. So finding the point is easy because it'll have some rational coordinates. Okay. And so let's say it has 3 3/4. Then we know that that's 3 3/4, and somewhere here is 3. So we can find the integer points. So this may be 3 3/4, whereas this may be -1. And so we know everything between -1 and 3 3/4, and we can identify all the integer points. And because x is at integer coordinates, we know that this point here has integer coordinates, so therefore that entire vertical line has a integer x coordinate, right? So it's just the y coordinate that we have to worry about, and this guy may have non-integer y coordinate. And so we go and figure out where the nearest integer y coordinate is, and that'll be our first point. And we can actually physically count by brute force all the points that are sitting on that vertical line. And then we would have at least one step, we would be one step ahead. Then when we come to this horizontal line, again we would find this point which would have possibly a rational, a non-integer x coordinate, and we would find all the integer points on its way. And then once you have this, then counting this should be somewhat easy, I think. Well, should be doable, not easy.
So how those counting would work out?
Yeah. So some of that count, yeah, it can't. You're right. It can't be brute force. But if I know the x coordinate of this, and if I know the x coordinate of this, this is integer, this is non-integer. All I have to do is to take a subtraction and do a floor, and I get the integer value. That'll tell me how many points are here. Done. Right?
But what about the points inside that triangle?
Yeah, that I think is doable. So essentially what we're saying is the following. Hold on. So we are saying the following. We have a triangle where this here has this is 0. Think of this as origin or some integer. This is some rational value on the x value, but it's still on the x-axis. And here is another rational value, I don't know, p, on the y-axis. And we're asking how many integer points are here. And I'm claiming that this is easy to do. Why am I saying this? Look, it's easy because the highest one here is going to be floor of p, right? So I know that there are floor of p points over here. Correct? Then because I know the slope of this line, I know where this is going to meet that line, and so I can figure out how many vertical lines you'll have before it goes down by 1. There must be a simpler way, but I'll try and see if I can come up with a formula for just this problem.
Does it just go down by 1?
It'll go down by 1, but you don't know how many times it'll stay the same. So that's what you have to kind of figure out. It won't go down by 1 in each one. If the slope is exactly 45 degrees, then it goes down by 1 after every one. But then it may take a while before it goes down if it's flat, if it's more flat. Yes, Yash?
Is there any formula if the triangle is a right angle triangle?
This is a right angle triangle. That's why I liked your idea, because with right angle triangles, especially those that are aligned to the x and y axis, it should be a lot simpler. I'm claiming, I'm going to brashly claim that there is a formula for this, and we can figure that out. So I'd suggest you try this out. If we can, you can't see my finger. If you can figure out the number of integer points in this triangle, then we should be able to solve the problem.
I hope that would be easy. Like if I have a right angle triangle and I can create a rectangle out of it. And,
Yeah.
divide all
So
the
let's assume this is the problem you're given. So imagine that this is the problem you're given. Okay, you're told that you have a right triangle at the origin. This one is at 0, 0. This one is at r0, and this one is at 0, p, where p and r are real numbers. They are rational numbers, not integer. May not be integers. And you're told the slope of this line. Let's say you're given this. Actually, you don't even need the slope of the line because it's just p divided by r, right? So that's also easy. So yeah, imagine that you're given this information. You just want to count how many integer points there are. If you can do this, then I think we can do the rest. We'll follow this up next time. Let me stop here. Thank you. Ricky, you caused us a lot of trouble.
Yeah, I didn't check it. Only one team got this problem.
Yeah?
And then my team.
It was fun.
Yeah. This was deceptively hard.
Maybe there's an easier way to do it, perhaps, right?
From the score, I don't think so.
Oh, okay.
Just my guess.